So in this video, we will do an example using Fourier series. So just to remind you, we had some region of space that had some pattern on it. We said we could write this pattern in terms of a bunch of sines and cosine waves, an infinite number of them. And this also works for any repeating pattern. If this repeated, this would be the same function right there. So usually they use Fourier series for repeating patterns, but if this is your entire pattern, it would work also if you didn't care about the space outside. And so what you always want to find is, you want to find these coefficients. You want to find A naught, A sub n, and B sub n. And here is the equation for A naught for the first term. Here is for the mth term in this quantity right here. And this one is for the B sub mth term right there, for that quantity right there. So I'm just going to do an example right here of one, just so you see how it works. Let's just say we have a function that looks like this. It goes down, and then it repeats itself, and then it goes down and repeats itself. So, and we'll call this length right here, we'll call this distance 2. And we'll call this distance 1. So then it's going to repeat itself again, and it could have repeated itself before. We want to write this as a bunch of sines and cosines. Now, first of all, we can see that the period is 2L. So in our case, 2L is 2, or L is equal to 1. So every place you see an L, when I work it out, I'll just put in 1. And then if I wanted to get the function f of x for this right here, I can just see that the slope is 1 and it goes through the origin. So this is just 1/2 x. So there's my function. And I want to write this function as a bunch of sine waves. Okay. So what do? We just need to find these three things right here. So first of all, let's find our A naught. Our A naught is equal to the integral, so it's 1 over 2L times the integral from 0 to 2L, but L is 1, so it's from 0 to 2. L is 1, so it's 1/2. F of x, there's my f of x, 1/2 x dx. Okay, so I'm just plugging in this formula right here. Okay, so I can pull this out in front, so A naught equals 1/4, and then the integral of x dx is x squared over 2, evaluated from 0 to 2. That's just 4 over 8, which is 1/2. So we got the first, A naught. It's just, this one's going to be 1/2 for that picture right there. Now we can find all of our the mth term, an arbitrary mth term. So it's just 2, L was 1, so if L is 1, this whole thing is 1. So we don't even have to put anything there. So it's just the integral from 0 to 2L, but L is 1, so it's to 2. F of x, which is 1/2 x, and A sub m has the cosine of m pi x over L dx. So we just have to solve that. I can bring out the half, and it looks like if I bring out the half, I'll use parts on the other, this whole piece right here, and we'll let u equal x, and we'll let dv equal the cosine of m pi x over L dx. And so du is equal to dx, and v is equal to integral of the cosine is the sine. Oh, I don't need the L in there because the L is 1. So again, I can just take that away. I can take that away. So we just get the integral of this is just sine of m pi x all over m pi. Okay, so that means a sub m is equal to, I pulled out the half, then we got uv, so we got this times this. So we got x times the sine of m pi x all over m pi, evaluated from 0 to 2, minus the integral from 0 to 2 of v, which is the sine of m pi x over m pi. I guess I can bring that out in front, 1 over m pi, du, which is dx. Close that off. Okay, and so this term, we already know what that's going to be. That's just the integral of the sine of m pi x over L, and we already knew, we said that one was 0. So this whole term is just 0. Now over here, when we plug in the 0, that's definitely 0. And when we plug in the 2 here, the sine of 2m pi is also 0. Sine of pi is 0, 2 pi, 3 pi, m pi is 0. So this whole term is 0. So a sub m is 0. So now we've got a naught, which was 1/2, and we've got this one, which is 0. So we don't have any a sub m's. That means there are no cosines in this wave right here. I'd imagine there wouldn't be, because if you had a cosine would be down here. How could you make it 0 here? You can't have a bunch of cosines here. So, okay, and now we just need to get the b sub m. Okay, so again, we're just using this thing. L is 1, so this is just 1 from 0 to 2. So this is just the integral 0 to 2 of f of x, which is 1/2 x times the sine of m pi x. L was 1 dx. Okay, so it looks like we'll do parts on this one also. U is equal to x, dv is equal to the sine of m pi x dx. Du is equal to dx. V is equal to the sine m pi x, sorry, it's not the sine. Integrating the sine is minus the cosine m pi x all over m pi. Okay, so now b sub m is equal to 1/2 the integral. We got uv, so we got x minus cosine m pi x all over m pi, evaluated from 0 to 2, minus the integral from 0 to 2 of v du. This, I can pull out the minus 1 over m pi, that's plus 1 over m pi. Cosine m pi x du dx. Okay, close that off. Okay, well, same reason we said this one is 0. This is cosine of m pi x over L. We said over an entire period, that's always 0. So this term is 0. this term over here, when we plug in 0, we get 0. But now all we have to do is we just have to plug in 2 right here. Well, when you plug in the 2's drop out. So we get a minus cosine. We're plugging in 2m pi all over m pi. Well, what is the cosine of 2m pi? Well, when m is 1, the cosine of 2 pi is 1. When m is 2, cosine of 4 pi is 1. 6 pi is 1. This is always 1 right there. So this is just minus 1 over m pi. So that's my b sub m. This is minus 1 over m pi. So now that I've found them all, I can write out my f of x. My f of x is a naught, which is 1/2 plus the sum from n equals 1 to infinity of a sub n's, but well, my a sub n's, all of them are 0. a1, a2, a3, they're all 0. So that's 0. And then all I have is this term plus the b sub m's, which is minus. So that means this is going to become a minus. I can pull out the pi. I can't pull out the m. Now in this case, since this is for the nth case right here, so I'm going to be putting n on the other side here. So this is 1 over pi sine of n pi x all over n right here. Because this was just for an individual one right here, when n for the arbitrary one. So here, this is just the sum of them all. So if I were to plot this function out right here, take all those infinite number of terms, it should look like this. Just to see if that does, I did that on Mathematica. You come over here. So here you can see I defined my f of x. There's from the Fourier series. There's your a naught, there's your a n, and there's your b n. So I said, let's do the one I just did right here. And so there's my function, x over 2, 1/2 x. I just drew this other part just for visual purposes. We don't use it right there, but this is the function right there, the 1/2 x. So I said, first, let's get my a naught. Well, that was just what we did up there. It was 1/2 times the integral of x over 2 dx. And then we wanted to get your a sub n's. So here was the integral of f of x cosine. I had to tell Mathematica that n was an integer because it only works for integers. And it gave me 0 for all of them. And then I said for the nth one, I just put the sign in there. And it gave me minus 1 over n pi, just like we had. So this was that function I just wrote. 1/2 minus 1 over pi sine n pi x over n. And I put a second parameter here. How many terms do I want to take right here? So if I said, let's just plot out the 1/2 in the first term, when n is equal to 1. This is what you get. Doesn't look like that picture up there. But let's say we pick on the next term. The 1/2, and the first 2 terms over here in this sum. And it's starting to look a little bit like my y equals 1/2 x. Let's take more terms. To the third right here. So now it's getting a little bit more like the term we have up here. Let me do it from 4 all the way to 10. I'll put them on top of each other. And so it's starting to look a little bit more. And let me put the original wave on so I can compare. There's the original one. But I've only gone up to 10 so far. But let's go up to 20. Here's 20 right here. As you can see right here, we're getting very close. And here I said, let's go out to 50 terms. 50 terms, it's getting very close. It has a tough time on real sharp edges. I have to go up to more and more terms right there. And then I said, let's try a different function. 4 minus x squared. Well, that's just an upside down parabola. Looks like this. 4 minus x squared, and then I said repeat it, and so on. And so here, 2L is equal to 2, so again, L is 1. Again, we can get our A naught. In this case, it was 8/3. We could get your A sub n's, and we could get your B sub n's. Now I have both. And now, again, I can combine them, put them all into my function, and now plot them out. Here's just the first term. This doesn't quite look like my original picture. Here's the first 2 terms. Now it's starting to look like it. The 3 terms, here I went up to 10 terms again, and showing the original wave. It's kind of hard to see the original wave. And then here's the 50 terms. And so then I said, well, let's just make one that I can just pick any function I want, like the parabola, and pick how many terms I want. As I add more and more terms, you see how it gets closer and closer to the true value. If I pick a sawtooth, that's kind of the one we just did. If I add more and more terms here, it gets closer and closer to the real function right there. So this is very helpful with Fourier series. You can make any sort of pattern you want with just a bunch of sines and cosine waves. Okay.